Imagine you have one chance to send a message across the galaxy, and it can carry a single number. The recipients have physics, but they have never heard of a meter or a second. Send them the speed of light, and all that arrives is a meaningless string of digits, because a meter is a decision a committee made in revolutionary France. But there is one number you could send that needs no translation at all. It is built from 4 quantities that each carry units, combined so that every unit cancels exactly. It is roughly 1/137, and it sets the strength of electromagnetism, which means it sets the size of every atom, the possibility of chemistry, and whether your hand rests on the blanket instead of passing through it. Any civilization anywhere that has looked closely at atoms will have found it, and will be exactly as unable to explain it as we are. By the end of tonight, you will know exactly why explaining this one small number would amount to explaining the universe. Before we begin, if this kind of slow, unhurried exploration is how you like to fall asleep, a like or a subscribe would mean a great deal. It is a small thing for you, and it means the world to me. Now, let's ease in. There is a number that a certain kind of physicist keeps within sight of their desk. Not a formula, not an equation, not a portrait of anyone famous. A number. It is written out in different ways by different people. Some write it as a decimal, 0.00729735, and let the digits trail off. Some write it as a fraction, 1/137. Some just write the 137 and leave the rest implied, the way you might write a name rather than a description. Richard Feynman explained the habit in 1985 in a book he wrote for people who had never studied physics. He said that this number has been a mystery ever since it was discovered more than 50 years earlier, and that all good theoretical physicists put this number up on their wall and worry about it. He was not being poetic. He meant it as a description of a professional practice, the way you might say that all good carpenters keep a level within arm's reach. The word to hold on to in that sentence is worry. Physicists are not short of things to find beautiful. There are equations that people have tattooed on themselves, symmetries that have made grown adults cry, results so elegant that the mathematics feels like it is showing off. None of those get put on the wall. This number gets put on the wall because it is unfinished business, and looking at it is a way of not letting yourself forget that it is unfinished. Paul Dirac, who wrote down the equation that predicted the existence of antimatter before anyone had seen any, called the explanation of this number the most fundamental unsolved problem in physics. Not one of the problems, the most fundamental one. Dirac was a man so economical with speech that colleagues invented a unit of measurement for it, and he chose to spend some of his very few words on this. Wolfgang Pauli went further, and in a stranger direction. Pauli was the man who worked out the exclusion principle, the rule that forbids 2 electrons from occupying the same state, which is the only reason matter takes up space at all. Without Pauli's rule, you would fall through the floor, and the floor would fall through the ground, and the ground would collapse into something very small and very hot. He was also famous for being the most caustic critic in physics. He is the person who, when handed a paper he considered worthless, is supposed to have said that it was not even wrong. That man said that when he died, his first question to the devil would be, "What is the meaning of the fine structure constant?" He did not say his first question to God. He said the devil, which is either a joke about where he expected to end up, or a joke about who would actually know. Either way, he had decided in advance that of all the things he might ask at the end of his life, this was the one he wanted answered first. So we have 3 of the most formidable minds of the 20th century, none of whom agreed with each other about very much, all circling the same number, and all describing the experience in the language of unpaid debt. That is worth stopping over for a moment. Physics does not usually work like this. The whole point of the enterprise is that mysteries get solved and become chapters in textbooks and stop being mysteries. This one has been on the wall for more than 100 years. The number is called the fine structure constant, and physicists write it with the Greek letter alpha. That name is a historical accident, and a slightly misleading one, because it tells you only where the number was first noticed, not what it is. We will get to where it was noticed. But it is worth saying plainly at the start what the number does, because otherwise the obsession sounds like mathematics rather than like something that concerns you. Alpha is the strength of electromagnetism. That is it. That is the whole job. It is the number that says how strongly electric charge and light are able to affect each other. And since electromagnetism is the force responsible for essentially every experience you have ever had, that makes alpha the setting on which ordinary reality runs. Consider what is actually built out of electromagnetism. Every chemical bond in your body is an electromagnetic arrangement of electrons. Every photon that has ever entered your eye was emitted and absorbed electromagnetically. The reason your hand does not pass through the blanket is electromagnetic repulsion between the electron clouds on the surface of your skin and the electron clouds on the surface of the fabric. The rigidity of the floor, the tension in a rope, the sound of a voice, the operation of every nerve in your brain, the light from the screen if there is one still on in the room, the fact that atoms hold together into molecules, and molecules hold together into things, all of it is one force, and alpha is the dial that force is set to. Turn that dial, and the world does not get slightly different. It stops. And here is the situation, stated as plainly as it can be stated. We know the value of that dial setting to about 81 parts per trillion. We can predict things using it to a precision that has no equal anywhere in science. We built the entire modern world on knowing it, and there is no theory, anywhere, that explains why it has the value it has rather than some other value. It cannot be derived. It can only be measured. Physics has to go and ask the universe what the number is, write down the answer, and carry on. Now, plenty of numbers in physics have to be measured. The mass of the electron has to be measured. The mass of the top quark has to be measured. That is not by itself scandalous. What makes alpha different is a property that sounds like a technicality and is not one at all. Alpha has no units. The speed of light is a number of meters per second. Change your mind about how long a meter is, and the number changes. The gravitational constant carries kilograms and meters and seconds inside it, and it too shifts if you shift your definitions. Planck's constant carries joule seconds. Every one of those famous numbers is partly a statement about the universe and partly a statement about the measuring conventions of a species of primate on one particular planet. Alpha is not. Alpha is assembled from 4 quantities that each carry units, combined in a particular way, and when you carry out the combination, every unit cancels against another unit exactly. Nothing is left but a bare number. It would be the same number for a physicist in the Andromeda galaxy who had never heard of a meter. It would be the same number for something that measured length in body lengths and time in heartbeats. It is one of the very few things we know about the universe that contains no trace of us at all. That is the property that turned a spectroscopic detail into a century-long obsession. A number that carries units is a conversation between nature and our conventions. A number with no units is nature talking to itself, and we are overhearing it. So the question that a physicist stares at when they look up from their desk is not really, why is alpha equal to this rather than that? The question underneath it is larger and much less comfortable. If this number is genuinely free of human convention, and it appears throughout physics in places that have nothing to do with each other, and no theory we possess can produce it, then what exactly is our theory missing? What would you have to already understand in order to be able to work this number out from first principles? The answer to that question is the reason for the promise in the title of this video, and it is a large promise, so it will not be cashed until the very end. But by the end of tonight, You will know exactly why, explaining one small number, with no units, sitting near 1 over 137, would amount to explaining the universe. Before any of that, though, we have to go back to the moment somebody first noticed it, and it did not arrive as a grand principle. It arrived as an irritation, a set of measurements that were slightly wrong, in a way that would not go away. Everything we know about the composition of the universe beyond arm's reach comes from a single trick, and the trick is embarrassingly simple. You take light and you spread it out. Pass sunlight through a prism and it fans into a band of color. That much has been known since Newton. But if you do it carefully enough, with a good enough instrument, using light that has come from a hot gas rather than from a hot solid object, you do not get a smooth band at all. You get a set of sharp, bright lines standing at particular positions, with darkness between them. Hydrogen produces one arrangement of lines. Helium produces a different arrangement. Sodium produces a pair of yellow lines so distinctive that they are used to calibrate instruments to this day. The lines are not decoration. They are the direct visible consequence of what is happening inside the atom. An electron sitting in an atom cannot have just any energy. It is restricted to particular levels, like steps on a staircase, with no ramp. When an electron drops from a higher step to a lower one, the energy difference has to go somewhere, and it leaves as a single particle of light, carrying exactly that much energy. Energy fixes color, so each possible drop produces light of one precise color, and the pattern of lines is a direct readout of the staircase inside that particular element. This is why we can say what a star is made of without going there. Starlight arrives carrying the fingerprints of everything it passed through, and everything that emitted it. The helium in the sun was identified in sunlight in the 1860s, decades before anyone found any on Earth. It was named after the sun for exactly that reason. When astronomers today announce the composition of the atmosphere of a planet orbiting another star, they are doing the same thing Newton did with a prism, with better equipment and more patience. Explaining those lines was the engine that drove physics into the quantum era. In 1885, a Swiss schoolteacher named Johann Balmer, working from 4 measured wavelengths in the visible hydrogen spectrum, found a formula that reproduced all 4. He had no idea why it worked. He was a man in his 60s looking for a pattern in a handful of numbers, and he found one that turned out to be a window into the structure of matter. In 1913, Niels Bohr produced a model that explained Balmer's formula by simply decreeing that electrons could only occupy certain orbits and no others. The decree had no justification. It worked anyway, spectacularly, for hydrogen. Then in 1926, the Schrödinger equation did the job properly, replacing the decree with a wave and extended it to atoms with more than one electron. Each of these steps was driven by the same thing, somebody looking at a set of sharp lines and demanding to know why they sat where they sat. And then, as the instruments improved, the lines misbehaved. The first problem was that the positions were slightly off. Not wildly off, not the kind of wrong that tells you a theory is broken, but consistently and reproducibly a little away from where calculations said they should be. That is the most annoying kind of discrepancy in all of science, because it is too small to ignore and too small to obviously mean anything. The second problem was worse and much more interesting. As spectroscopes got sharper, physicists discovered that some of what they had been calling a line was not a line at all. It was 2 lines, sitting so close together that every previous instrument had smeared them into one, a doublet. 2 nearly identical energies, where the theory predicted a single energy, separated by a gap so small it had been invisible for the entire history of the subject. This splitting was given a name that has stuck ever since: fine structure. The gross structure of a spectrum is the main pattern of lines, the thing Balmer and Bohr explained. The fine structure is the hairline crack running through each of those lines when you look closely enough. If you want an example you have very likely seen with your own eyes, look at an old sodium street lamp, the kind that throws that flat orange-yellow light that makes everything underneath it look colorless. That light is almost entirely two spectral lines, sitting side by side at about 589 nanometers, and the reason there are two of them, rather than one, is fine structure. Those two lines are close enough that they were treated as a single line for years, and far enough apart that a decent modern spectroscope separates them easily. Every time you have walked under one of those lamps, you have been standing in light whose color is set, in part, by the number this video is about. The measurement that revealed it came from a pair of names you probably know for something else entirely. In 1887, Albert Michelson and Edward Morley, working in Cleveland, built an interferometer of extraordinary sensitivity and used it to resolve the red line of hydrogen into a doublet. That same year, with the same style of instrument and the same obsessive precision, the two of them performed the experiment they are actually remembered for, the attempt to detect the motion of the Earth through the ether, which returned nothing. Think about that year for a moment. In one 12-month stretch, two men in Ohio produced the null result that would help demolish classical physics and clear the ground for relativity, and also produced the fine measurement that would eventually hand physics a number it still cannot explain. One of those results told us something was wrong with the old picture. The other planted a problem that would outlive the new picture too. The gap they had found was tiny. The red hydrogen line sits at about 656 nanometers, and the fine structure splitting inside it amounts to roughly 1 part in 50,000 of the line's own frequency. To resolve that, you have to be able to distinguish two colors that differ by an amount no eye could ever detect and no ordinary instrument could reach. It took the best interferometry on the planet to see it. And once seen, it could not be unseen. Every element showed it. The staircase inside the atom had a structure inside its structure, an additional layer of fine detail nobody had predicted, and the theory of the day had nothing to say about it. This is the point where it is worth remembering what we are actually chasing. The number this video is about, the strength of electromagnetism, the setting on which the ordinary world runs, was not discovered by anyone thinking about the strength of electromagnetism. It was discovered by people trying to account for a hairline gap between two red lines emitted by hot hydrogen. Nobody was looking for a universal constant. They were looking for the reason their arithmetic did not match their photographic plates. That is how this kind of discovery usually goes, and it is a useful thing to hold on to. The great constants of nature do not announce themselves. They turn up as residue, as the leftover, as the part of the measurement that would not reconcile, as the little bit that some very patient person refused to write off as experimental error. There is also something worth noticing about the scale of the thing. The energy of the whole hydrogen line represents the electron falling a long way down its staircase. The fine structure splitting is a small correction sitting on top of that, and the size of the correction is not arbitrary. It is governed by a factor, and the factor turns out to be the same for every element and every line. That is the observation that starts everything. It is not that the splitting exists, it is that the splitting is always the same fraction of the thing it is splitting. Whenever you find a fixed ratio in nature that shows up regardless of what system you are looking at, you have found something that is not about the system. You have found something about the rules. So, by the early years of the 20th century, physics had a very specific and very narrow problem sitting on its desk. Something was splitting spectral lines by a definite, universal, small amount, and whatever it was, applied everywhere. What was needed was somebody willing to take the two newest and least settled ideas in all of physics, the quantum, which was 15 years old, and relativity, which was 11, and force them into the same calculation. That person was in Munich, and when he did it, he pulled out a number that made no sense at all. Arnold Sommerfeld ran the Theoretical Physics Institute in Munich, and by the middle of the 1910s, it was probably the best place in the world to be a young person with an unreasonable idea. He was not primarily a discoverer, he was a teacher, and an extraordinary one. Over his career, he was nominated for the Nobel Prize 84 times, more than any other physicist in history, and he never won it. 4 of his students did. If you were going to hand somebody an unexplained hairline gap between 2 red lines and ask them to account for it, Sommerfeld was the correct person to hand it to. His approach in 1916 was to take Bohr's model and stop making it so tidy. Bohr had electrons moving in perfect circles at fixed radii, which was already an arbitrary decree, and Sommerfeld's first move was to allow ellipses as well. Planets do not move in circles. There is no reason electrons should either. An ellipse of the same average size as a circle has the same overall energy in a simple treatment, so at first this changes nothing observable. His second move is where it gets interesting. He remembered that an electron in an elliptical orbit does not travel at a constant speed. It moves fastest when it swings closest to the nucleus and slowest at the far end, exactly the way a comet does. And an object that changes speed in a system governed by relativity does not simply change speed, its mass changes with it, because relativity says that a moving object carries more inertia than a stationary one. This was 1916. Special relativity was 11 years old. Quantum theory of the atom was 3 years old. Almost nobody was combining them, because they came from different directions and answered different questions, and the people working on one were often not the people working on the other. Sommerfeld put them in the same calculation and asked what happened. What happened was that the energy of an orbit stopped depending only on how big the orbit was. It started depending also on how elongated it was, because a more elongated orbit means a faster swing past the nucleus, which means a larger relativistic mass correction, which means a slightly different energy. Orbits that had been identical in Bohr's model separated by a small amount. Levels split. And when the electrons dropped between split levels, they emitted light at slightly different energies, which is to say, single spectral lines became doublets. He had explained fine structure. But that is not the part that matters for us. The part that matters is what showed up when he worked out how big the splitting would be. The size of the gap between the split lines came out governed by a particular combination of quantities. Take the charge on the electron and square it. Divide that by 4 times pi, by the permittivity of free space, by Planck's constant, and by the speed of light. That combination, whatever it turned out to be numerically, set the scale of the entire effect. Now, physicists see combinations like that all the time. Constants get multiplied and divided in the course of a derivation, and nobody thinks twice about it. The reason this one stopped people is something we will come to properly in a moment, but here is the short version. The charge of an electron is measured in coulombs, the speed of light in meters per second, and the other two carry their own units too, and yet when you combine them the way Sommerfeld's formula combines them, every unit disappears. What is left is a number with nothing attached to it, and that number is about 1 over 137. Sommerfeld did not present it as a mystery, he presented it as a ratio, and a rather sensible one. It was, in his picture, essentially the speed of the innermost electron, expressed as a fraction of the speed of light. That framing is still accurate and still useful. In the ground state of hydrogen, the Bohr model electron circles the nucleus at roughly 2,188 kilometers per second, which sounds enormous until you compare it with light and find it is smaller by exactly that factor. So one honest description of the fine structure constant, right from the beginning, is that it is how slow an electron is compared to light. For a while that seemed like the whole story, and it made the number feel domesticated. It was a velocity ratio in a particular model of a particular atom. Interesting, not profound. Except there was a problem with Sommerfeld's derivation that nobody could see at the time, because the missing piece had not been discovered yet. Sommerfeld's account of fine structure had no spin in it. Electron spin was not proposed until 1925, 9 years later, and it turns out that the real physical origin of fine structure is not simply the relativistic mass change of a fast-moving electron. It is a combination of that effect with something else entirely. The electron behaves as though it carries a small magnet, and as it moves through the electric field of the nucleus, it experiences a magnetic field, and the energy of that little magnet depends on which way it is pointing. Two orientations, two energies, two lines. There is a third contribution as well, a subtle correction arising from the fact that a quantum electron cannot be treated as sitting at a single point. None of that was in Sommerfeld's calculation. He had one of the three effects, described in the wrong language, in a model of the atom that would shortly be discarded entirely, and his formula for the size of the splitting was correct. It was correct for 12 years, before anybody could say why. In 1928, Paul Dirac wrote down an equation for the electron that was properly consistent with relativity from the start, rather than being a quantum model with relativity bolted onto the side. When he solved it for hydrogen, the fine structure came out, and so did spin, not put in by hand, not assumed, but emerging from the mathematics as an unavoidable property of any particle the equation could describe. Dirac had not been trying to explain spin. He had been trying to write a consistent equation, and spin arrived unrequested, along with an even stranger prediction about states of negative energy that turned out to be antimatter. Dirac's solution reproduced Sommerfeld's formula for the fine structure splitting exactly. Two completely different pictures of the atom, one of them wrong, giving the same answer. There is a sequel to this that is worth 2 sentences now and will matter later. Dirac's equation was itself not the end of the story. In 1947, Willis Lamb and Robert Rutherford measured 2 particular hydrogen levels that Dirac's equation said should have exactly the same energy, and found that they did not. They were separated by about 1057 megahertz. That gap could not come from Dirac's theory at any level of care, and closing it required inventing the full quantum theory of the electromagnetic field. Hans Bethe produced the first serviceable estimate of it on a train ride home from the conference, where the result was announced. So the pattern repeats, an unexplained small gap between 2 lines, and the entire next layer of physics falling out of the attempt to account for it. This kind of thing happens more often in physics than anyone finds comfortable, and it should be a small warning to us for the rest of tonight. Getting the right number does not mean you have understood the mechanism. Sommerfeld had a number, an accurate number, a number that matched every measurement anyone could make, and he had it for the wrong reason. Inside a model of the atom that would be gone within a decade. The number survived. The picture around it did not. Hold on to that, because we are going to meet several other people over the course of this video who produced the right number for reasons that turned out to be nothing at all, and it will be tempting to laugh at them. They were doing what Sommerfeld did. Sommerfeld simply got lucky. Meanwhile, the combination he had written down was quietly outgrowing the problem it was invented for. It had been derived to explain a hairline gap in a spectrum. Within a few decades, it would be turning up in calculations that had nothing to do with spectra, nothing to do with hydrogen, and in some cases, nothing to do with atoms. But before we follow it there, we have to look properly at the thing that made physicists nervous in the first place. The thing I skipped over a few minutes ago. Because when you actually work through what happens to the units in Sommerfeld's combination, something occurs that has no parallel among any of the other famous constants of nature. Every measurement humans make is partly a statement about the universe, and partly a statement about us. A meter is not a natural object. It began as an attempt to divide the distance from the North Pole to the equator into 10 million parts, a decision made by a committee in revolutionary France, and it has been redefined several times since by other committees. A second is inherited from Babylonian arithmetic, which divided things by 60 because 60 has a lot of factors. A kilogram was, until embarrassingly recently, a specific lump of platinum and iridium sitting under 3 glass bells in a vault outside Paris, and every kilogram on Earth was defined as being however heavy that lump happened to be that day. The lump drifted. Its official copies drifted differently. For most of the 20th century, the mass of everything in the universe was formally pegged to a slowly changing object in a French basement. So when a physicist says the speed of light is 299,792,458 meters per second, they are telling you two things at once. They are telling you something about light, and they are telling you about the pole to equator survey and the Babylonians. Change the conventions, and the number changes. It would be a completely different number in furlongs per fortnight, and no physics would be different. This applies to almost every celebrated constant. The gravitational constant carries meters and kilograms and seconds inside it. Planck's constant carries joules and seconds. The charge on an electron is a number of coulombs, and a coulomb is defined by reference to other human decisions. Each of these numbers is a hybrid, nature and convention, laminated together so tightly that people forget the second layer is there. Now take the 4 quantities in Sommerfeld's combination and follow the units through. The elementary charge is squared, so it contributes coulombs squared. The permittivity of free space carries a compound unit that includes an inverse of coulombs squared, and those cancel exactly. What is left over involves energy and length on one side, and the reduced Planck constant carries energy multiplied by time, and the speed of light carries length divided by time. And when you divide by both of them, the energy cancels the energy, the length cancels the length, and the time cancels the time. Nothing survives. Not one unit, not approximately, not to within measurement error, but exactly and structurally, because that is how the algebra falls out. 4 quantities, from 3 different branches of physics, electromagnetism, quantum mechanics, and relativity, assemble into something that carries no reference to any human decision whatsoever. What you are left with is a number that would survive the loss of everything we invented. Burn every meter stick. Forget the second. Lose the platinum lump. Abolish the coulomb, the joule, the Kelvin, and the entire apparatus of measurement that our species built up over 400 years. And this number is exactly what it was. It is not a fact about our instruments. It is a fact about the universe, sitting there whether or not anyone ever builds an instrument at all. There is a way of feeling how odd that is, and it involves aliens. Suppose you had one chance to send a message across the galaxy, and the message could be extremely short, a handful of bits, enough to encode one number. The recipient is intelligent and has physics, but shares no history with us, no units, no language, nothing. You want them to know that whatever sent this understood something about the world. You might think of sending the speed of light, but the speed of light is a number of meters per second, and they have never heard of a meter or a second, so what arrives is a meaningless string of digits. You would have to send the definition of a meter first, which requires sending a definition of something else, and you can see where this goes. The gravitational constant is worse, because it needs mass as well. Planck's constant needs mass too. Now send them 1 over 137. They know, not because they can decode our units. There are no units to decode. They know because a civilization that has looked closely at atoms anywhere in the universe will have found this number and will have wondered about it, and will very likely have some equivalent of a physicist who keeps it near their desk. It is possibly the only piece of information we could send that requires no translation at all. Being unitless is not, on its own, remarkable. There are lots of unitless numbers in physics. The proton is about 1,836 times heavier than the electron, and that ratio has no units either, because the masses cancel. The coefficient of friction of a wooden block on a wooden ramp has no units. You can manufacture dimensionless numbers all day by dividing any quantity by another quantity of the same kind. What makes this one different is that it will not stay where it was put. The proton-to-electron mass ratio shows up when you are calculating things involving protons and electrons, which is where you would expect a proton-to-electron mass ratio to show up. It behaves. The fine structure constant does not behave. It was found in the gap between two red lines, and it then appeared in the size of atoms, in the speed of electrons, in the energy of light, in the probability of a particle interaction, in calculations about materials, in calculations about stars. It kept turning up in rooms it had not been invited to. There is a stronger version of this point, and it has been argued forcefully by the physicist Michael Duff, among others, in a published exchange with two colleagues who disagreed with him about how many fundamental constants there really are. Duff's position is that questions like, what if the speed of light had been different, are not merely difficult to answer, they are not questions at all. Suppose the speed of light doubled overnight. What would you notice? You would measure it with rulers and clocks are themselves made of atoms whose properties depend on the same constants. So everything would shift together, and every measurement would come out identical. Nothing observable would have changed. A change you cannot in principle detect is not a change. But if alpha changed, you would notice, because alpha has no units for a shift in conventions to hide inside. Spectral lines would move relative to each other. Chemistry would alter. On this view, the dimensionless numbers are not merely the tidiest constants. They are the only ones about which the question could it have been otherwise is even meaningful. Which means alpha is not one interesting constant among many. It is one of the few places where the question is real. And there is a modern coda to all this that is, if you think about it for long enough, faintly unnerving. In 2019, the International System of Units was rebuilt from the ground up. Humanity had grown tired of defining its measurements by physical objects and historical accidents, so it did something decisive. It took a set of fundamental constants and declared them to be exact by definition. The speed of light, exact by decree. Planck's constant, exact by decree. The elementary charge, exact. Boltzmann's constant, exact. From those fixed values, every unit in the system is derived. The platinum lump was retired. The meter and the second and the kilogram became consequences of constants rather than the other way round. It was, in a real sense, the moment our species finished the job of taking itself out of its own measurements. And here is what happened to alpha. Because the charge and Planck's constant and the speed of light are now exact by definition, the uncertainty that used to live in them had to go somewhere. It went into the permittivity of free space, which had previously been exact and is now a measured quantity. And the uncertainty in it is precisely, exactly, the uncertainty in the fine structure constant. We spent 2 centuries defining our units. We finished the job by pinning the last of them to constants of nature. And when the dust settled, the one thing that had refused to be defined away, the one quantity that still had to be gone and measured, the residue left at the bottom of the entire enterprise, was this number. You cannot legislate it. You cannot choose it. You cannot make it go away by being clever about definitions. It simply is what it is, and the only thing you are permitted to do about it is find out. So we have a number with no units, that appears in places it has no business appearing, that survives every attempt to define it out of existence. The obvious next question is the one Sommerfeld never asked, because he thought he already knew the answer. Where, exactly, does it turn up? Because the list is longer and considerably stranger than a splitting between 2 spectral lines. The reason this number graduated from curiosity to obsession is not the spectral lines. It is what happened afterwards, over the following decades, as physicists worked on problems that had nothing to do with hydrogen and kept finding the same number waiting for them at the end of the calculation. Here is a first example, and it is a strange one because it connects two things that ought to have nothing to say to each other. Take two electrons and hold them a certain distance apart. They repel each other, and that repulsion carries a certain amount of energy, a purely electrical quantity, a matter of static charges pushing. Now separately, forget the electrons and think about a single particle of light with a wavelength that matches the distance you chose. That photon carries an energy too, determined entirely by its wavelength, which is a quantum mechanical matter with no charges involved at all. Compare the two energies. The electrical repulsion is smaller than the photon's energy by a factor of about 137, and it does not matter what distance you picked. Move the electrons further apart, and both energies drop, but the ratio does not budge. A static push between two charges and a quantum of light are locked together in a fixed proportion, and the proportion is our number. Here is a second. In the Bohr model of hydrogen, the electron in its lowest state circles the nucleus at about 2,188 kilometers per second, roughly 700 times faster than a rifle bullet, fast enough to cross the United States in under 2 seconds. Divide that by the speed of light, and you get alpha, precisely. Sommerfeld noticed this one first, and it is still the cleanest one-line description of what the number is. It is how slow the innermost electron is compared to light. Here is a third. That same electron is bound to the proton by 13.6 electron volts of energy, which is the amount you would have to supply to tear the atom apart. The electron also has a rest energy, the energy locked in its own mass by the famous relation between mass and energy, and that is a much larger quantity. Compare the two, and the binding energy is smaller by a factor of 137 squared over 2. Not 137 this time, 137 squared. And here is a fourth, which is the one I find hardest to shake. Imagine shrinking down toward an electron, and pay attention to the scales you pass through on the way. Let the room around you fall away for a moment, and go down into a single hydrogen atom, the simplest object in the universe, one proton and one electron, the thing that most of the mass in existence is still made of. You begin at the size of a hydrogen atom, about half an angstrom across, 500 millionths of a millimeter. At this scale, the electron is not a dot anywhere. It is a standing cloud of probability wrapped around the proton, denser near the middle, fading outward with no edge anywhere. This is the size that matters for chemistry, the size that determines how atoms pack together into molecules, and how molecules pack together into everything else. It is, in a real sense, the size of the ordinary world. Now shrink by a factor of 137, and you arrive somewhere quite different. This is the electron's reduced Compton wavelength, and it marks the scale at which the question, "Where is the electron?" stops being answerable in the ordinary way. Try to pin an electron down to a region this small, and the energy required to do the pinning is comparable to the energy locked in the electron's own mass, which means your attempt to locate the particle starts producing new particles instead. The universe answers your question by making more electrons. This is the boundary where quantum mechanics on its own stops being enough, and you need quantum field theory. Shrink by a factor of 137 again. You have arrived at what is called the classical electron radius, about 2.8 femtometers, a couple of thousandths of a trillionth of a meter. This length was invented before quantum mechanics existed, by physicists who imagined the electron as a tiny charged sphere and asked how big the sphere would have to be for its own electrical energy to account for its mass. That picture is wrong. The number is still meaningful, and it turns up in the formula for how strongly light scatters off free electrons, which is, among other things, why the sky above you is blue, and why the light in the early universe could not travel freely until the plasma cooled. 3 lengths, the size of the ordinary chemical world. The scale where locating a particle creates particles. The scale from a discarded 19th century picture that stubbornly refuses to stop being useful. 3 quantities, from 3 different eras of thinking about the same particle, arranged on a ladder, and each rung is 1 factor of alpha down from the last. Nobody designed that ladder. Nobody arranged for the spacing to be even. It fell out. There is one more appearance worth mentioning, because it is the least romantic and the most useful. In a quantum Hall experiment, a sheet of electrons confined to 2 dimensions and cooled almost to absolute zero develops an electrical resistance that comes in exact, discrete steps. Those steps do not depend on the shape of the sample, or its purity, or the temperature within wide limits. They are determined by pure constants, and the resistance quantum that sets their size is directly related to alpha. This is so reliable that it was used for decades as the world's practical standard of electrical resistance, and it provides one of the independent routes by which alpha is measured. Somewhere right now there is a laboratory holding a chip at a fraction of a degree above absolute zero, and the number coming out of it is the same number Sommerfeld pulled out of a hydrogen spectrum in 1916. And the list keeps going. The fine structure splitting that started this whole story scales as alpha to the 4th power, which is why it is so small and took a century of instrument building to see. The rate at which excited atoms emit light depends on alpha. The strength with which a magnetic field shifts atomic energy levels depends on alpha. The behavior of electrons in solids, the properties of certain exotic materials, the precise resistance measured in a quantum Hall experiment. Alpha, alpha, alpha. It is worth saying that none of these appearances were predicted in advance by anyone. In every case the sequence was the same. Somebody set out to calculate something specific, ground through the algebra, and found the same combination of charge and Planck's constant and the speed of light sitting in the answer, uninvited. The number was not sought. It kept being found by people who were looking for something else, in problems that had no connection to each other, except that they all involved charged things and light. At some point, a pattern this persistent stops feeling like a pattern and starts feeling like a message. That is the state physicists found themselves in through the 1920s and 30s, and it is why the obsession set in. It was not that a number was unexplained. Physics is full of unexplained numbers, and mostly copes fine. It was that this particular number appeared to be structural, as though it were not a property of any of these systems, but a property of the stage they were all standing on. Dirac's phrase, remember, was the most fundamental unsolved problem in physics. Not an unsolved problem, not an important one, the most fundamental. That is a claim that this number is not sitting on top of physics but underneath it. So what is it? What is the thing that all of these calculations have in common, such that the same number falls out of every one of them? There is an answer. It is genuinely satisfying, and by the standards of quantum physics, it is remarkably simple to state. It was not available to Sommerfeld, or to Bohr, or to anyone until the 1940s, because it required the invention of a whole new way of doing physics. And when it arrives, it does 2 things at once. It explains completely why this number keeps appearing in so many unrelated places, and it makes the underlying mystery worse, not better, because it turns a question about a coincidence into a question about the most basic fact there is. To understand what the fine structure constant actually is, you have to give up on a picture you almost certainly still carry around, which is the picture of forces as things that push and pull. In the modern account, there is no pushing. When 2 electrons repel each other, nothing reaches across the gap and shoves. What happens is that one electron emits a particle of light, and the other absorbs it, and the exchange of that light carries momentum from one to the other, and the result looks from the outside like repulsion. Electromagnetism is not a force in the way a hand on a door is a force. It is a conversation conducted in photons. Once you accept that, a question appears immediately, and it is the question this whole video has been walking toward. How likely is that conversation to happen at all? Put an electron somewhere, have light go past it. How often do they notice each other? That likelihood has a name. It is called the coupling strength of the electromagnetic interaction, and it is the fine structure constant. That is the answer. Alpha is the probability that an electron and a photon interact. It is about 1 in 137. Everything else follows from that, and it is worth walking slowly through why, because it explains the entire list of coincidences we just went through. Richard Feynman gave physics a way of picturing this, and it is one of the few genuinely famous pieces of notation in the subject. To calculate what happens when particles interact, you draw diagrams. Lines represent particles moving through space and time. Wavy lines represent photons. Where a photon meets an electron, the lines join at a point, and that point is called a vertex, a place where the conversation happens, where light is emitted or absorbed. The rule is that you do not draw one diagram, you draw every diagram, every possible way the interaction could occur, however baroque. Two electrons approaching each other might exchange a single photon, which is the simple case, or they might exchange two photons, or one electron might emit a photon and reabsorb it before the other one ever notices, or a photon might briefly turn into an electron and a positron, which then annihilate back into a photon, or all of these at once, in combinations of increasing absurdity. Every one of those histories contributes to the final answer, and the way you get the answer is to add them all up. That is not a metaphor for how the calculation works. That is literally how the calculation works, and it produces results of extraordinary accuracy, which is one of the reasons quantum physics is difficult to argue with, even when it is difficult to accept. And now the crucial part. Every vertex in every diagram, every single point where a photon meets an electron, contributes a factor to the calculation. That factor is the square root of alpha, about 0.085. Square it, because interactions come in pairs of vertices in the simplest cases, and you have alpha itself. So alpha is not a number that shows up in the answer. It is a number that gets stamped onto the calculation at every place where light and matter touch. Now go back through the list from a moment ago, and it stops being a list of coincidences. Why does the size of an atom involve alpha? Because an atom is an electron and a nucleus in continuous electromagnetic conversation, and the strength of that conversation determines how tightly the electron is held, which determines how far out it sits. Why does the speed of the innermost electron involve alpha? Same reason. The orbital speed is set by the balance between the electron's quantum reluctance to be confined and the electrical attraction pulling it in, and the strength of that attraction is alpha. Why does the ratio between electrical repulsion and photon energy involve alpha? Because that ratio is a comparison between the electromagnetic interaction and the light quantum it is conducted with, which is exactly what alpha measures. Why is the fine structure splitting proportional to alpha to the fourth power? Because it is a small correction on top of a structure that is already electromagnetic, and each additional layer of electromagnetic subtlety costs additional factors of the coupling. Every single one of them is the same fact wearing a different hat. There was never a mysterious recurrence. There was one number, the strength of the only force that matters at these scales, showing up wherever that force does anything, which is everywhere because that force does everything. There is a way of writing this down that makes the point even more sharply. Physicists working in this area rarely bother with meters and seconds. They work in what are called natural units, where the speed of light and the reduced Planck constant are both simply set equal to 1, on the grounds that they are conversion factors between things that are secretly the same. Do that, and Sommerfeld's formidable-looking expression collapses to something almost insultingly plain. Alpha is the square of the electron's charge, divided by 4 pi. That is the whole thing. Strip out every unit humans ever invented, and what is left is the charge on an electron, squared. Which tells you something worth pausing on. The mystery of the fine structure constant is, at bottom, the mystery of why the electron carries the amount of charge it carries. Not why charge exists, not why it comes in discrete lumps, which is its own unanswered question. Why the lump is that big. This is the deflation, and it is a real deflation. If somebody tells you that the fine structure constant is mystical because it turns up in so many unrelated formulas, the correct response is that the formulas are not unrelated. They are all electromagnetism. But hold on, because the mystery has not gone anywhere. It has only moved, and it has moved somewhere much harder to reach. We have replaced the question, why does this number keep appearing, with the question, why is the strength of electromagnetism 1 in 137? And that question is worse than the one we started with, for a reason that becomes obvious the moment you try to imagine answering it. There is no obvious upper limit. There is no obvious lower limit. There is no principle anyone has found that says the coupling has to be small, or has to be positive, or has to be anything at all. It could apparently have been 1 in 10, or 1 in a million, or 1 in 1. In each case, you would have a perfectly self-consistent theory of electromagnetism, mathematically fine, internally coherent, describing a universe that does not look remotely like this one. Nothing in the structure of quantum electrodynamics prefers our value. You measure alpha, you put it in the theory, and the theory works. Change alpha, put the new value in, and the theory still works. It just describes somewhere else. And notice that this is not a temporary state of ignorance of the ordinary kind, where we simply have not measured something well enough yet. We have measured it superbly. The theory is not waiting on better data. The theory has no opinion. That is what physicists mean when they call something a free parameter. It is a knob with no stop on it, and the position of the knob has to be read off the universe rather than worked out. The standard model of particle physics has somewhere between 19 and 26 of these, depending on how you count neutrino masses. 19 numbers, minimum, that the most successful theory in the history of science cannot produce and must be handed. Alpha is one of them, or rather alpha is built out of 2 of them, which is a distinction that will matter enormously by the end of this video. But there is something else about the smallness of this particular number, and it is the strangest thing in this whole story. It is not just that alpha happens to be small. It is that if alpha were not small, you and I would not be able to do physics at all. Not because we would not exist, though that is true too, and we will come to it. For a much narrower and more embarrassing reason. The entire method I have just described to you, the drawing of diagrams and the adding up of possibilities, only works because the number is small. Make it large, and the method collapses, the calculations become impossible, and the most precisely verified prediction in the history of human knowledge simply never happens. We did not earn our understanding of the universe. We were handed the conditions that made it possible, and the size of that gift is written into the same number nobody can explain. Consider what it means to add up every possible way an interaction could happen. There is an infinite number of ways. That is not an exaggeration or a figure of speech. You can always draw a more complicated diagram. One more photon exchanged, one more particle pair flickering into existence and out again, one more loop of increasing intricacy. The set of possible histories connecting a beginning to an end is genuinely without limit, and the correct answer requires all of them. An infinite sum is not automatically a disaster. Mathematics handles infinite sums routinely, provided the terms get small fast enough. Add a half, then a quarter, then an eighth, and keep going forever, and you arrive at 1. The sum converges because each term is a fixed fraction of the last. That is exactly what happens in quantum electrodynamics, and the fixed fraction is our number. Every vertex costs a factor of the square root of alpha. A diagram with 2 extra vertices, 1 more photon exchanged, is therefore suppressed by a full factor of alpha relative to the simpler one, about 1 part in 137. The next level down is suppressed by another factor of 137, and so on. So the infinite sum behaves. The simplest diagram gives you the answer to about 1%. Add the next layer, and you are at 1/100%. Add another, and you are chasing the 6th decimal place. Each additional layer of complexity is enormously harder to compute and contributes enormously less, and at some point you stop because you have reached the precision anyone can measure. This is why quantum electrodynamics is the most accurate theory human beings have ever constructed. Not because it is deeper than the others, because the coupling is small enough that the sum settles down. To see how much of a gift that is, look at what happens when it is absent. The strong nuclear force, which holds quarks together inside protons and neutrons, has a coupling strength that is, at everyday energies, roughly of order 1. Not 1/137, 1. Which means that a diagram with 2 extra vertices is not suppressed at all. It contributes about as much as the simple one, and the next is as large again, and the next, and the sum does not converge, and cannot be truncated, and the entire method breaks down completely. Physicists working on the strong force cannot draw a few diagrams and stop. They have to abandon the approach, and instead simulate the force by brute computational force, chopping space-time into a grid and running enormous calculations on supercomputers for months. And even then, the mass of the proton is known to a fraction of a percent, not to 12 decimal places. Same universe. Same mathematics, same physicists, often literally the same people. The only difference is the size of the coupling constant, and on one side of that difference sits the most precisely tested prediction in the history of science, and on the other side sits a problem so hard it consumes supercomputer time by the century. Here is what our side of that line looks like in practice. The electron behaves as a tiny magnet, and the strength of that magnet was predicted by Dirac's equation to have a particular value. Quantum electrodynamics says the answer is slightly different, because the electron is constantly emitting and reabsorbing photons and briefly surrounding itself with particle pairs, and all that activity nudges its magnetism. Calculating the size of the nudge means summing diagrams, layer by layer. The first layer was done in 1947 and fits on a page. The second layer took years. By the time physicists reached the 5th layer, 10th order, in the technical counting, the calculation required evaluating 12,672 distinct Feynman diagrams. That work took a small group of people a substantial portion of their careers, and could not have been completed by hand in a human lifetime. And in 2023, a group at Northwestern measured the electron's magnetism experimentally to a precision of about 13 parts in 100 trillion, roughly 1 part in a million. Theory and experiment agree. Try to hold the size of that for a second. It is the equivalent of predicting the distance from New York to Los Angeles in advance, from pure theory, and being right to within the width of a human hair. There is nothing else like it anywhere in science, and it exists for one reason and one reason only, which is that the number we have been talking about all night is small. There is a subtlety in that agreement that matters for later, so let me plant it now. The theoretical prediction for the electron's magnetism has alpha inside it. So if the only way you knew alpha were by measuring the electron's magnetism and solving backwards, the agreement would be circular. You would not be testing anything. You would be defining alpha and calling it a result. That is why the independent measurements of alpha are so important. If you can determine alpha by some completely different route, using atoms and lasers and nothing to do with magnetism, Then you can feed that value into the prediction and compare against the measurement honestly. The comparison becomes a real test of whether the theory is complete. Remember that, because in the final part of this video, it becomes the sharpest live question in the entire subject. There is also a mirror image of the strong force problem that is worth one sentence. The strong coupling behaves in exactly the opposite way to ours at high energy. It gets weaker as you push harder, so that quarks slammed together at enormous energy behave almost as though they were free. That property won a Nobel Prize in 2004, and it is the reason particle physicists can calculate anything at all about the inside of a proton. That is worth sitting with, because it inverts something most people assume about science. We tend to think that our understanding of the universe is a measure of how clever we have been. Some of it is, but a large part of the reason physics has been possible at all is that we were handed a universe in which the dominant force at our scale happens to be weak enough to approximate. A civilization living in a universe with a larger alpha, assuming there could be one, which is a separate problem, would not simply have found physics harder. They would have found the entire method unavailable. Their electrons would have been uncalculable. Their most precise number would have been a rough estimate, not because they were less intelligent, but because nobody had left the door open. We did not earn that. We inherited it. And now the twist, which is one of my favorite facts in this entire subject. In 1952, Freeman Dyson published an argument that the quantum electrodynamics series does not actually converge. Ever. It only appears to. His reasoning was elegant and slightly frightening. Suppose, he said, that we flipped the sign of the coupling so that like charges attracted rather than repelled. In such a world, empty space would be catastrophically unstable. It would be energetically favorable for the vacuum to spontaneously produce enormous numbers of electrons and positrons, separate them into clumps, and never stop. There would be no stable state at all. And a theory that is a disaster for a negative coupling cannot be smoothly well behaved at a coupling of zero, which is exactly what a genuinely convergent series would require. So the series is what mathematicians call asymptotic. It gets better and better and better, and then, past a certain number of terms, it starts getting worse, and eventually it diverges to nonsense. The rough point where it turns around is set by the coupling. It is approximately 1 over alpha terms in. About 137. There is a ceiling on how well quantum electrodynamics can ever be calculated by this method, and the height of the ceiling is the same number that made the calculation possible in the first place. The gift and the limit are the same object. The number that opened the door also marks how far down the corridor anyone can walk. Nobody is anywhere near that ceiling, incidentally. 5 layers in, out of roughly 137 available, and each one has cost decades. It is a wall we can see and will almost certainly never reach. But it is there, and it is made of the same thing the floor is made of. Which brings us to the point in this story where the ground genuinely gives way, because everything I have told you so far about this number being fixed, precise, and constant is about to turn out to be, at best, a convenient simplification. Let us step back for a moment and put the pieces together, because we are about halfway through and the picture so far is fairly clean. There is a number, roughly 1 over 137. It was found in the hairline gap inside a spectral line by a man in Munich who combined relativity with the quantum in 1916 and got the right answer for reasons that turned out to be incomplete. The number has no units, which means it contains no trace of any human convention and survives every attempt to define it away. It appears throughout physics, and it appears there because it is the coupling strength of electromagnetism, the probability, roughly 1 in 137, that an electron and a photon notice each other. Its smallness is why we can calculate anything, and the same smallness sets a ceiling on how far the calculation can ever go. Nothing in our best theory says why it takes the value it does. That is a tidy story, and every word of it is true, and I now have to tell you that one of those words is doing a great deal of quiet work. The word is constant. Alpha is not a fixed number. Its value depends on the energy of the interaction you are examining, and it grows as that energy increases. The number everybody quotes, 1 over 137, is its value in the limit of very low energy. Push harder, and you get a different number. The reason for this is one of the strangest confirmed facts in physics, and it starts with the observation that empty space is not empty. According to quantum field theory, the vacuum is not a void with nothing in it. It is a seething thing. Particle-antiparticle pairs are continuously appearing and annihilating, borrowing energy from the uncertainty in the fabric of the field and paying it back before anything can be measured. Electrons and positrons flicker into being and vanish, everywhere, all the time, including in the space between these words and inside the room you are lying in. You cannot catch them. Individually, they are unobservable by construction, but collectively, they do something, and the something is measurable. Take a real electron and put it into that vacuum. The virtual positrons, flickering around it, are positively charged, so they are attracted toward it. The virtual electrons are repelled and drift outward. The result is that the real electron becomes wrapped in a faint, constantly reshuffling cloud of opposite charge, and that cloud partially cancels it. From a distance, the electron looks weaker than it really is. The vacuum is screening it. This is called vacuum polarization, and it is not a theoretical flourish. It is measured routinely. Now think about what that means for the strength of the electromagnetic force. If you interact with the electron from far away, gently, at low energy, you are looking at it through the full thickness of the screen, and you see the screened, diluted charge. If you hit it hard, with high energy, you penetrate further into the cloud, you get inside more of the screening, and you see more of the bare charge underneath, which means the force is stronger at short range than at long range, over and above the ordinary falling off with distance. The coupling itself changes. At everyday energies, alpha is 1 over 137.036. At the energy of a Z boson, around 91 gigaelectron volts, which is the scale probed by large particle colliders, alpha has climbed to about 1 over 128. That is a change of roughly 7%, and it has been measured directly by watching how the rate of electron scattering changes as collision energy is turned up. This is not a prediction awaiting confirmation. It is an experimental fact from the 1990s. So the fine structure constant, the great fixed number of the universe, the thing 100 physicists have kept on their wall for a century, is not fixed. It is a curve, and the famous value is just the point where that curve flattens out at the bottom. It is worth being clear that this is not a case of the number being uncertain or badly measured. Both values are known with great precision. They are simply different values of the same quantity, measured under different conditions, exactly as a physicist would expect. The running of the coupling is one of the central predictions of quantum field theory. It was worked out in detail decades before it could be tested properly, and when the tests came, they matched. This is the theory working, not failing. But it does something uncomfortable to the way the number has been talked about for a century. When Dirac called the explanation of alpha the most fundamental unsolved problem in physics, and when Feynman told people to put it on their wall, the thing they had in mind was a specific value with specific digits. That value is real, and it is the one that governs the world you live in, because you and everything around you exist at the flat bottom of the energy scale. But it is a local reading, not an absolute. It is the answer to the question, how strong is electromagnetism when nothing much is happening? Follow the curve upward, and it takes you backward in time. In the first instance after the Big Bang, Energies were vastly higher than anything a collider can produce, and alpha would have been correspondingly larger, climbing toward 1. At those energies, electromagnetism was not even a separate force. It was fused with the weak nuclear force into a single unified electroweak interaction, and the distinction between them, along with the whole idea of an electric charge with a particular strength, did not yet exist in the form we know. Then the universe expanded and cooled. Energies dropped. The unified force separated into the two we now recognize. Electromagnetism went its own way, and alpha slid down its curve as the temperature fell, and it kept sliding, and eventually the universe cooled to essentially nothing on this scale, and alpha came to rest. At 1/137.036, and nobody knows why it stopped there. That is the sentence I want to leave in the room for a moment, because it is not the same statement as the one we started with. Earlier the mystery was, why does this number have this value? Which sounds like the sort of thing that might have a neat answer waiting somewhere. The real mystery is, why did a quantity that was falling stop falling at a particular place, when nothing in the theory specifies where the floor is? There is no known principle preventing it from having continued all the way to 0. And an alpha of 0 is not a slightly different universe. It is no electromagnetism whatsoever, no attraction between electrons and nuclei, so no atoms, no chemical bonds, so no molecules, no chemistry, no biology, no light being emitted or absorbed by anything, so no stars visible, and no eyes to see them with. Charged particles would drift through each other without interacting, and the universe would be a thin, cold fog of unattached fundamental particles for the rest of time. What you thought was a fact about reality is a resting position, and there is no known reason it should have rested somewhere survivable. This also, quietly, executes an entire genre of proposed explanations, and we will meet the casualties in a couple of parts' time. If you have ever come across a formula claiming to derive 137.036 out of pi and square roots and geometry, the running of the coupling is the fact that kills it, and it kills it without needing to check the arithmetic. Any such formula has to answer a question it cannot survive. Derive the number at what energy? A quantity that changes with the circumstances of the measurement is not the sort of thing that falls out of pure mathematics. Pi does not care how hard you hit it. So we have lost the fixed number and gained something stranger, a quantity that moved and settled, and whose settling place happens to permit atoms. The obvious next question is whether it has really stopped moving, because if alpha slid down a curve over the history of the universe, the possibility opens up that it is still drifting, very slowly, or that it sits at slightly different values in different places. That would change the entire nature of the problem. A constant that needs explaining is one kind of question. A field that needs a mechanism is another kind entirely. And it turns out we can check, not with theory, with rocks. In 1972, at a uranium processing facility in the south of France, a technician ran a routine check on a batch of ore and found a number that should not have been possible. Natural uranium comes in two main varieties. The overwhelming bulk of it is uranium-238. A small fraction is uranium-235, which is the variety that will sustain a chain reaction and is therefore the variety everyone cares about. That fraction is not approximately fixed. It is fixed, everywhere, to a degree that borders on the boring. Every sample of uranium ore ever measured, from any mine on any continent, from meteorites, from the lunar surface, contains 0.720% uranium-235. The reason is simple. Both varieties were forged in stellar events long before the Earth existed, and both have been decaying ever since at their own steady rates. The ratio between them is set by the clock. Every atom of uranium on the planet has been sitting through the same 4.5 billion years, so every sample gives the same answer. The sample in front of the technician read 0.717%. The shortfall was 0.003 of a percentage point, 3 parts in 1,000 of the number itself. If you handed that discrepancy to a careless person, they would call it instrument drift and go to lunch. Instead, somebody chased it, and they chased it partly because there is precisely one process known to remove uranium-235 from uranium while leaving uranium-238 behind, and that process is a nuclear reactor, which raises an alarming question about a batch of raw ore, because the ore in question had come out of the ground in Gabon, in West Africa, from a mine called Oklo, and nobody had put a reactor there. The investigation that followed found 17 separate zones in the Oklo deposit where the uranium had been depleted, and where the surrounding rock was full of the specific fission products that a reactor produces, and nothing else does. The conclusion was not in doubt for long, because there was no other conclusion available. Roughly 1.7 billion years ago, that seam of rock had gone critical on its own. Picture the situation, because it is worth doing properly. You are standing on a continent that has no name and will not have one for a very long time. There are no animals. There are no plants on the land. Nothing green anywhere. No trees. No grass. No soil in the sense you would recognize it. The atmosphere has only relatively recently acquired appreciable oxygen, which is itself a recent catastrophe from the point of view of the organisms that were here first. The most sophisticated life on the planet is single-celled and lives in water. Below your feet is a seam of uranium ore, unusually rich, and this matters because 1.7 billion years ago, the natural abundance of uranium-235 was much higher than it is today. It decays faster than its heavier sibling, so the further back you go, the more of it there was. Back then the ore was, without any human intervention whatsoever, at roughly the enrichment level that a modern power station requires. Groundwater seeps down through the seam. Water is a moderator. It slows neutrons down, and slow neutrons are far more likely to split uranium-235 than fast ones. With enough water in the pore spaces, the seam reaches the point where each fission triggers another. It starts. The rock heats. Nothing announces it. There is no flash and no explosion, because this is not a bomb. It is a slow simmer distributed through tons of ore. The temperature climbs, and the water in the pores boils away, and with the moderator gone, the reaction stalls and dies. The rock sits, cooling, for hours. Groundwater seeps back in. The reaction restarts. That cycle, run, boil dry, stall, cool, refill, run, repeated for something on the order of a few 100,000 years, at an average output of around 100 kilowatts. Enough to run a small building, buried in the ground, in absolute silence, with no organism anywhere on Earth complex enough to notice, on a planet whose land surface was bare rock from horizon to horizon. And it left a receipt. That is where this connects back to the number we have been following all night, and the connection was spotted in 1996 by Thibaut Damour and Freeman Dyson, the same Dyson from the divergence argument a few minutes ago. A working reactor is a delicately balanced thing, and the balance depends on nuclear resonances, particular energies at which a nucleus will absorb a neutron with enormously enhanced probability. One of the most important of these belongs to samarium-149, which sits in the fission product mix and acts as a powerful neutron absorber. Its resonance sits at a very low energy, and the position of that resonance depends on a delicate cancellation between two much larger quantities: the strong nuclear binding and the electromagnetic repulsion of the protons crammed into the nucleus. Electromagnetic repulsion, which means the position of that resonance depends on alpha. And here is the beautiful part. Because the resonance energy is a small residue of a near cancellation between two large numbers, it is extraordinarily sensitive. A tiny fractional change in the electromagnetic contribution shifts the resonance by a much larger fraction of its own value. Move alpha slightly, and the resonance walks away from the energy of the neutrons in the reactor, and the samarium stops absorbing them the way it did, and the isotope ratios left in the rock come out different. The isotope ratios in the rock are measurable today. They have been sitting in Gabon for 1.7 billion years, and stone does not have opinions. Darmour and Dyson ran the calculation backwards. Given what the rock actually contains, how much could alpha have differed 1.7 billion years ago and still produce this signature? The answer that came out, and that has been refined by others since, is that alpha has changed by less than about 1 part in 10 million over roughly 2 billion years. Let me put that beside the alternative. If alpha were drifting at even 1 part in a million per billion years, that seam would have left a different fingerprint. It did not. A puddle of groundwater in West Africa, doing something no rock is supposed to do, in an era before anything on land was alive, is one of the tightest constraints in all of fundamental physics. Nobody designed the experiment. Nobody ran it. It ran itself, recorded its own results in the mineral structure, waited 1.7 billion years, and was read by a technician who refused to round 0.003% down to zero. There are a couple of details about Oklo that are worth keeping, because they make the thing more real rather than less. The first is that some of the fission products are still essentially where they were made. Elements that were created inside those reactor zones 1.7 billion years ago have, in several cases, failed to migrate more than a short distance through the surrounding rock in all the time since. That fact has been studied seriously by people who need to know whether it is safe to bury nuclear waste in geological formations, and Oklo is the only natural long-term experiment anybody has. The second is a caveat, and it should be stated because the honest version of a good result always includes one. The Oklo constraint is powerful but narrow. It applies to a 2 billion year window, in one location, in a system where several constants of nature enter the calculation together. So what is really being constrained is a combination rather than alpha in perfect isolation. Untangling that requires assumptions. Different groups analyzing the same reactor zones have produced results that differ in their details, and one analysis has even reported a small non-zero shift rather than a flat null. The consensus reading is that alpha has not moved, but the honest summary is that a rock is a very good clock and a slightly ambiguous thermometer. That covers 2 billion years, which is a substantial fraction of the age of the Earth and a small fraction of the age of the universe. To go further back, and to ask whether alpha is the same in other parts of the universe rather than merely at other times, you need something that reaches much further than a mine. You need light that has been traveling for most of the history of everything. And when a team went looking in exactly that light in 1999, they found something. A quasar is the brightest sustained thing in the universe. It is a supermassive black hole in the center of a young galaxy, tearing apart everything that falls toward it, and the matter spiraling in gets so hot on the way down that the resulting glare can outshine the entire galaxy around it by a factor of 100 or more. Quasars are visible across almost the whole observable universe, which means that when you look at one, you are looking at light that left before the Earth existed. That light does not travel through nothing. On its way to us, it passes through gas clouds, the tenuous, cold remains of matter drifting between galaxies. Each cloud absorbs particular wavelengths, the ones matching the energy gaps in the atoms it contains, and it stamps dark absorption lines into the quasar's spectrum. By the time the light reaches a telescope on Earth, it is carrying a set of dark bars, each one a signature of a cloud it crossed, at a distance and an era we can determine. And here is the point. Some of those absorption lines are fine structure doublets, split pairs, the same kind of hairline gap that Michelson and Morley resolved in Ohio in 1887, and that Sommerfeld explained in 1916. And the size of that gap depends on alpha, as it was in that cloud at that moment, billions of years ago. Which means a spectrograph is a time machine for one specific number. In 1999, a team including John Webb and Michael Murphy did exactly this, with data from the Keck telescopes in Hawaii. They compared the fine structure and absorption systems from 10 to 12 billion years ago against laboratory values, and they reported that alpha appeared to have been very slightly smaller back then, by about 1 part in 100,000. That is a small number, but it is not nothing. A change in alpha of 1 part in 100,000 over 10 billion years is enormously larger than what Oklo permits over the last 2 billion, which would already make it interesting, and it would mean that the strength of electromagnetism is not a constant at all, but a slowly evolving quantity, which would mean there is a field somewhere driving the evolution, which would mean an entire layer of physics nobody has found. It is worth understanding why this measurement is so difficult, because the difficulty is the whole story. You are not comparing a line to itself, you are comparing the spacing between lines in a cloud 12 billion light-years away against the spacing between the same lines measured in a laboratory on Earth, and asking whether the ratio has shifted by 1 part in 100,000. That requires knowing the laboratory wavelengths to better precision than the astronomical ones, which is a whole separate field of work. It requires knowing that the cloud is not doing something unexpected of its own. A cloud with an unusual mix of isotopes, for instance, will produce slightly shifted lines for reasons that have nothing to do with alpha. And it requires the telescope itself to be telling the truth about which wavelength landed on which pixel, across the whole width of a detector, consistently, over years of observations. Every one of those 3 is a place where a false signal can be manufactured. The teams involved knew that perfectly well and spent enormous effort on all 3. In 2011, the same group went further. They combined the Keck data, which looks mainly at the northern sky, with data from the Very Large Telescope in Chile, which looks mainly at the southern sky, and they reported that alpha appeared to be slightly larger in one direction on the sky and slightly smaller in the opposite direction. A dipole, a cosmic axis, a preferred direction in the strength of electromagnetism, as though the universe were very gently tilted with respect to a quantity that is supposed to be the same everywhere. If that were true, it would be one of the most important results in the history of physics. It would mean the laws are not uniform. It would mean that the assumption underlying essentially all of cosmology, that physics is the same over there as it is here, is only locally true, and that we live in a patch. It would also mean that the reason alpha sits in the narrow range permitting atoms might simply be that we necessarily live in a region where it does. The claim was reported at around 4 standard deviations, which is respectable and short of the threshold physicists use for a discovery. And this is the part of the story I want to spend real time on, because what happened next is not dramatic and is much more instructive than the claim itself. Other teams looked, a group analyzing a separate set of very large telescope observations found nothing, no variation, consistent with alpha being flat. That is not by itself decisive, because different data sets and different methods can disagree honestly. Then, in 2015, came the audit. A careful study by Jonathan Whitmore and Michael Murphy examined the wavelength calibration of both instruments, the process by which a spectrograph decides which pixel corresponds to which wavelength. They found long-range distortions in that calibration, not random noise, but systematic drifts across the detector, on both telescopes, of a size fully capable of manufacturing a spurious signal comparable to the effect being claimed. Michael Murphy was a co-author of the original variation papers. He was, in other words, one of the people who had spent more than a decade building the case, and he participated in finding the flaw that most plausibly explains it away. That deserves more admiration than it usually gets. There is a picture of science as a contest in which people defend their positions until forced out of them. What actually happens at the highest level, quite often, is that the person who made the claim goes looking for the thing that would kill it, harder than anyone else does, because they are the one who understands the instrument well enough to know where to look. Since then, better behaved instruments have been turned on the problem. The espresso spectrograph on the Very Large Telescope was designed for extreme wavelength stability, and measurements toward well-studied absorption systems have come back consistent with no variation at all, at the level of about 1 part in a million. Other high-precision single-system measurements have done the same. The honest summary is this. The dipole has not been confirmed. Its most likely explanation is instrumental. The field has largely moved on, and the original result has never been formally retracted, because it was never fabricated. It was measured, carefully, by good scientists, using the best instruments then available, and the instruments turned out to have a flaw nobody knew about. That is what the correction of a scientific error looks like from the inside. It takes 16 years. It is conducted in technical papers about pixel calibration that nobody outside the field will ever read. There is no announcement, no retraction, no scandal, and no villain. It is slow, unglamorous, and largely performed by the people who had the most to lose. Meanwhile, the tightest limits on any drift in alpha now come from a completely different direction, and it is a nice inversion. Instead of looking billions of years into the past, you look at 2 clocks in a laboratory. Optical atomic clocks keep time by counting the oscillations of an atomic transition, and different transitions depend on alpha to different degrees. So, if you run 2 such clocks side by side, using elements chosen so that alpha affects them differently and alpha is drifting, the 2 clocks will slowly disagree. Run them for a few years and compare. They do not disagree. Current limits constrain the fractional change in alpha to better than about 1 part in 10 to the 18th per year. A precision so absurd that if alpha had been drifting at the maximum allowed rate since the Big Bang, it would have changed by a fraction of a percent. So the picture that emerges is not a drifting constant. It is a number that has apparently been sitting at exactly the same value everywhere anyone has looked, across almost the entire history and extent of the observable universe. Which brings the problem back into sharp focus and makes it worse rather than better. If alpha varied, we would at least have a phenomenon to explain, and a field to look for, and a mechanism to build. Instead, we have a number that does not move, does not depend on where you are, does not depend on when you are, and cannot be derived from anything, which is precisely the situation that has driven a number of extremely intelligent people to do something rather undignified. Sir Arthur Eddington was, by any reasonable measure, one of the great scientists of the 20th century. He worked out how stars generate and transport energy. He wrote the book that introduced the English-speaking world to general relativity. He led the eclipse expedition of 1919, whose measurements of starlight bending around the sun made Einstein famous overnight. He was not a marginal figure or a crank on the edges of the subject. He was at its center. And in the last 2 decades of his life, he became convinced that he could derive the fine structure constant from pure reason. His argument was that the inverse of alpha had to be exactly 136, and he constructed an elaborate framework to support it, involving the counting of degrees of freedom in a way that few of his contemporaries could follow, and none of them found persuasive. He also calculated, from the same framework, the total number of protons in the universe, 136, multiplied by 2, raised to the 256th power, which comes out around 1.5 times 10 to the 79th. He regarded these 2 results as connected, which is to say he believed the strength of electromagnetism and the amount of matter in existence were 2 faces of the same piece of arithmetic. Then measurements improved, and it became clear that the inverse of alpha was not 136. It was closer to 137. Eddington revised the derivation. The new version produced 137. His colleagues, who had been watching all this with the particular discomfort reserved for a great man's late work, began referring to him as Sir Arthur Adding One. The nickname is cruel, and it has stuck for 80 years, which tells you how badly the episode landed. His final book on the subject was published after his death in 1944, unfinished, and is now read almost exclusively by historians. The instinct to laugh at this should be resisted for one specific reason, which is that Eddington was doing something the entire profession would very much like somebody to succeed at. If a person could derive alpha from first principles, they would be the most important physicist since Einstein. Eddington simply tried, failed, and, this is the actual failure, could not stop. It is worth noticing what makes this failure mode specific to intelligence rather than to stupidity. Eddington's whole career had been built on exactly this move, taking a set of physical requirements, reasoning from them with great rigor, and arriving at a number that turned out to be right. That is how he worked out the internal structure of stars. That is how he understood the limit on how massive a certain kind of stellar remnant can be. A piece of work he then infamously refused to accept when a young Subrahmanyan Chandrasekhar pushed it further than he was willing to go. The instinct that produced his greatest results is the same instinct that produced his last, worst book. He did not become a different sort of thinker at the end of his life. He kept doing the thing that had always worked, on a problem where it does not work, and could not tell the difference from the inside. Nobody can tell the difference from the inside. That is the whole difficulty. He was not the last. In 1969, a Swiss mathematician named Armand Wyler published a short expression. It was built out of powers of pi and factorials and a piece of the geometry of certain symmetry groups, and it was not obviously connected to anything physical. What it did was evaluate to approximately 1/137.036. That was, at the time, the measured value of alpha to every digit anyone could establish. Consider what it is like to be handed that. Here is a short mathematical expression made of nothing but geometry, and it lands on the number that physics cannot explain. Not near it, on it, as far as anyone can tell. Freeman Dyson took it seriously enough to act. Dyson was at the Institute for Advanced Study in Princeton, one of the most rigorous minds in the field and, as we have seen, entirely capable of hard-headed arguments about why things do not work. He arranged for Wyler to be invited to Princeton, to the institute where Einstein had spent his last 2 decades, where Gödel walked the grounds, one of the small number of places on Earth where the phrase pure thought is a job description. Wyler came. The formula was examined. Physicists tried to find the physical reasoning underneath it, the argument that would say why the geometry of that particular symmetry group should determine the strength of electromagnetism. There was not one. The expression did not derive alpha. It resembled alpha. It had no mechanism, made no other prediction, and explained nothing that was not already the input. And as measurements of alpha improved through the 1970s and beyond, the value drifted away from Wyler's expression, digit by digit, until the match was gone. Wyler returned to Switzerland. The episode is a footnote now, occasionally cited as a cautionary tale, and the caution is worth extracting carefully because it is not the obvious one. The obvious lesson is that you should not do numerology. That is true, but useless, because nobody thinks they are doing numerology at the time. The real lesson is structural, and there are 2 halves to it. The first half is about freedom. If you are permitted to use any mathematical constants, any operations, any exponents, and any number of terms, you can hit essentially any target number to several decimal places. This is not a matter of opinion. It is a matter of counting. The space of short expressions is enormous, and the space of 6-digit numbers is not. A formula that matches alpha to 6 figures is therefore not evidence of anything on its own. The test of a formula is whether it predicts something you did not put in. Every one of these fails that test, without exception, and most of them do not attempt it. The second half is the one we uncovered a couple of parts ago, and it is fatal in a way the first is not. Alpha depends on energy. It is a curve, not a value, and the famous number is the flat part at the bottom. So when somebody presents you with an expression built from pi and factorials that evaluates to 137.036, the question that ends the conversation is not, is your arithmetic right? The question is, at what energy? Because pure mathematics does not know about energy. Pi is the same whether you whisper at it or fire it into a collider. A formula made of geometry can produce a number, but it cannot produce a number that changes when you probe harder, and alpha does exactly that. To derive alpha from mathematics, you would have to derive the entire running curve, including the point where it flattens, which means deriving the particle content of the universe, which means having the theory of everything already, at which point you would not need the formula. That single observation kills every attempt of this kind at once, without checking any of the arithmetic, and it was not available to Eddington, who died before the running of couplings was understood, and it was barely available to Wyler. It is also worth saying that the appetite for this never went away, it only moved. Every few years, somebody posts a new expression online, occasionally with real mathematical sophistication behind it, occasionally with none, and it circulates for a while among people who find the coincidence compelling. The response from physicists is not hostility, it is a kind of tiredness, because the same two objections apply every time, and neither of them is ever addressed. There is one more variant of this impulse worth mentioning, and it is the strangest, because it belongs to the most rigorous man in the story. 137 has a life outside physics. In Hebrew, gematria, where each letter carries a numerical value, and words can therefore be summed, the word Kabbalah, the name of the Jewish mystical tradition, comes to 137. That is a coincidence, and it is the kind of coincidence that occurs constantly in any system that assigns numbers to words. It would deserve no mention at all, except for who noticed it and what he did about it. Wolfgang Pauli was the most feared man in physics. He was feared for his mind, which was extraordinarily fast, and for his mouth, which was extraordinarily unkind. He worked out the exclusion principle at 24, the rule forbidding two electrons from sharing the same quantum state, which is the entire reason matter occupies space instead of collapsing into a point. He predicted the neutrino in 1930 on the grounds that energy had to be conserved and something invisible must be carrying it away, and apologized in the letter for proposing a particle he thought would never be detected. It was detected 26 years later. His reputation for cruelty was earned. He described a colleague's paper as so bad that it was not even wrong, a phrase that has outlived almost everything else he said. Younger physicists dreaded presenting in front of him. There was a joke that circulated for years about the Pauli effect, that experimental apparatus would spontaneously fail when he entered the building, purely out of self-preservation. This is the man who said that when he died, his first question to the devil would be about the meaning of the fine structure constant. And this is where the story takes a turn that the profession has never been entirely comfortable with. For more than 2 decades, Pauli corresponded with Carl Jung. Not casually, hundreds of letters, over 20+ years, running to a substantial published volume. It began in the early 1930s, when Pauli was in a bad state. His mother had killed herself, his brief first marriage had collapsed, he was drinking heavily, and his father suggested he see the psychologist in Zurich. Jung took him on, and then handed him to an assistant, on the reasoning that his own influence on a mind like that would be too strong. What came out of it was not a course of therapy, it was a correspondence between two people who both believed, seriously and in detail, that there might be a common root beneath the structures of the physical world and the structures of the mind. Jung thought the archetypes of the psyche were not merely psychological. Pauli thought the fact that abstract mathematics keeps turning out to describe nature was itself a fact requiring explanation, and not a comfortable one. They wrote to each other about dreams, about number, about the way scientific ideas arrive. Pauli recorded and analyzed more than 1,000 of his own dreams. He was careful about it, and he was aware of exactly how it would look. He kept the two halves of his working life mostly separate, and he did not entirely succeed. And sitting at the middle of all this was 137. Pauli knew about the gematria. He knew that the word Kabbalah sums to 137 in the system where Hebrew letters carry numerical values, and there is a well-attested story of the historian of Jewish mysticism, Gershom Scholem, being the one who pointed it out to him, and he did what a certain kind of mind does, with a coincidence of that shape, which is that he did not dismiss it, and he did not believe it either, and he carried it around for the rest of his life. I want to be extremely clear about what is being claimed here, because this is the part of the story most vulnerable to being told badly. There is no physics in the gematria. The Hebrew alphabet has nothing to do with the coupling strength of the electromagnetic interaction. The number 137 is not even the actual value of the inverse of alpha. The real number keeps going, 137.035999 and onward. And the roundness of the coincidence is a product of rounding. None of this is evidence about the universe. All of it is evidence about physicists. And that is the reason it belongs in this story. We have spent the last hour and a half with a number that will not explain itself, and I have shown you a series of first-rate minds walking up to it and coming away with nothing. Sommerfeld, who got it by accident. Eddington, who derived it twice and was wrong twice. Wyler, who matched it and could not say why. Pauli is the same story told from the inside. He is what it looks like when someone spends a lifetime unable to put a question down. On the 15th of December, 1958, Pauli was in the Red Cross hospital in Zurich. He was 58 years old. He had collapsed some days earlier with abdominal pain and had been admitted for what turned out to be pancreatic cancer, already far advanced. His assistant, Charles Enns, came to visit him. Pauli asked whether he had noticed the number on the door of the room. It was 137. He died in that room, a few days later. There is a detail in the room that makes it worse, or better, depending on your temperament. Pauli had been ill for a while, and had not wanted to make anything of it. He had given a lecture only weeks before. He had been working, as he always was, on the problem of whether the fundamental symmetries of nature could be derived rather than assumed, which is the same problem as the one on his wall, wearing different clothes. He had spent that autumn in a public and rather painful disagreement with Heisenberg about a proposed unified theory that Pauli had first been enthusiastic about and then decisively rejected. The last serious argument of his life was about whether a theory that produced numbers actually explained them. I am not going to tell you what that means, because it does not mean anything. Hospitals number their rooms sequentially, and there is nothing else to say about the mechanism. If you assembled every physicist who has ever worked on this problem and looked at every room number any of them ever occupied, some of them would be 137. And this is the one we tell stories about, because it happened to the right person. But something can be meaningless and still be true, and this one is true, and I find I cannot let go of it either. Here is a man who spent his professional life demanding that physics be free of nonsense, who invented an insult so precise it is still in use 70 years later, who could reduce a competent adult to silence in a seminar room, and who was, underneath all of that, unable to stop looking for meaning in a number, who told people that his first question in the afterlife would be about a number, and who ended up in a room bearing it. The weight of that is not that the universe was making a point. The weight is that the wanting was real. Pauli was not a mystic who happened to do physics. He was a great physicist whose greatness came from the same place as the wanting, because you do not spend 40 years worrying at a problem unless some part of you believes there is an answer down there and that it matters. The published correspondence with Jung has an English title, Atom and Archetype, and anyone expecting either a great physicist embarrassing himself or a secret mystical doctrine will be disappointed by it. What is actually in there is more interesting and more ordinary. A careful man trying to work out where the boundary of his own discipline is, and being honest with a correspondent outside it about the fact that he could not find one that satisfied him. Remember Feynman's line from the very beginning of tonight. All good theoretical physicists put this number up on their wall and worry about it. When you first hear it, it sounds like an anecdote, a charming bit of professional folklore, physicists and their quirks. It is not an anecdote, it is a description of what it costs. That is 100 years of the most capable people alive, spending part of their attention, every working day, on something that has never once given anything back. Dirac died without an answer. Eddington died without one, and with his reputation dented for having tried. Feynman died without one. Pauli died in room 137 without one. The number is still on the wall, and the wanting is not misplaced, which is the last thing I have to show you, because there is a reason this particular number is worth a century of anyone's attention, and it is not sentiment, and it is not numerology. It is that alpha sits at the exact point where our description of the universe stops being able to account for itself. Before that, though, there is one more thing to look at. We have talked all night about what this number is, and where it came from. We have not yet looked properly at what it does, at what would actually happen to the room you are lying in if the number were slightly different. Hold your hand a few inches above the bed, palm down, and let it rest there. The reason it stays where you put it, rather than sinking through the blanket, is that the outermost electrons in the atoms of your skin and the outermost electrons in the fibers of the fabric refuse to share space and push apart when they get close. That push is electromagnetic. Its strength is set by a probability of about 1 in 137, applied at an unimaginable number of points at once, all across the surface of your hand. Now lower it. The moment you feel contact is not contact. Nothing touches. The atoms in your hand come within a fraction of a nanometer of the atoms in the blanket, and the repulsion becomes strong enough to stop the approach, and your nervous system reports that as the feeling of a surface. Every surface you have ever felt has been that same probability, resisting you at a distance too small to imagine. So, change the number. Suppose alpha were a few percent larger. Electromagnetism strengthens. Electrons are held more tightly to nuclei, so atoms are drawn in and become smaller and more compact. That sounds harmless, but the outermost electrons are the ones that do chemistry. They are the ones available to be shared between atoms, and the sharing is what a chemical bond is. Bind them more tightly, and they become less willing to be shared. Chemistry becomes impoverished. The elaborate, loosely bound, endlessly reconfigurable molecules that living things are made of become harder to assemble and easier to break in the wrong ways. Now the other direction. Suppose alpha were a few percent smaller. Electromagnetism weakens. Electrons are held loosely, atoms swell, and molecules become unstable. The bonds are there, but they are not strong enough to survive ordinary thermal jostling. Complicated structures do not last long enough to do anything. It is worth pushing on the larger version of this too, because the small percentage changes are not the only thing on the table. Suppose alpha were much bigger, of order 1/10 rather than 1/137th. Electromagnetic repulsion inside a nucleus scales with it, and nuclei are already a fight between the strong force pulling protons together and their own charge pushing them apart. Strengthen the pushing enough, and heavy nuclei stop being stable at all. The periodic table gets shorter, then very short, and eventually there is nothing above the lightest few elements. No oxygen, no carbon, no iron, no rock. And there is the other extreme, the one we met a couple of parts ago when we watched alpha slide down its curve as the universe cooled. There is no known reason it had to stop, continue to zero, and electromagnetism simply ceases. Charged particles pass through one another without noticing. Nothing binds to anything. The universe becomes a cold, thin fog of unattached particles, expanding forever, with no structure in it of any kind and nothing anywhere that could be called an event. There is a narrow band between those two failures, and everything you have ever encountered lives inside it. The most quoted consequence involves carbon, and it is worth stating carefully because it is routinely overstated. Carbon is manufactured inside stars by a process that requires 3 helium nuclei to combine, and that process only works efficiently because of a fortunate coincidence in the energy levels of the resulting carbon nucleus. A resonance sitting at almost exactly the right energy. That resonance depends on the balance between the strong nuclear force and the electromagnetic repulsion of the protons packed together in the nucleus, which means it depends on alpha. Move alpha by a few percent, and the resonance moves off its sweet spot, and the rate of carbon production in stars falls sharply. Various groups have estimated the tolerance, and the figures cluster around a few percent in either direction before stellar carbon production is disrupted badly enough to matter. Now the caveat, which almost never gets included and should. That number is the output of a model, and the model contains assumptions about which other constants you hold fixed while you vary this one, about how stars behave under altered physics, about what counts as disrupted. Change the assumptions, and the tolerance changes. And the whole exercise varies one dial at a time, which is not obviously the right way to explore a space of possibilities where the dials may not be independent, as we have already seen good reason to suspect. The honest version is that alpha sits somewhere in a band. The band is not enormous, and the precise width is a modeling result rather than a measurement. There is a subtler point buried here that is easy to miss. The claim is not that a different alpha would produce a hostile universe. Hostile implies something that could be endured with difficulty. A universe without stable nuclei does not have chemistry that is hard. It has no chemistry. The failure is not a matter of degree. What is not in doubt is the direction of the conclusion. There are values of alpha that produce a universe with no atoms, and values that produce a universe with atoms but no interesting chemistry. And our value is not in either group. Come back to the hand on the blanket for a moment, because this is where the abstraction cashes out. The bed holding you up is not a solid thing resisting another solid thing. It is a very large number of electron clouds declining to overlap, each refusal governed by that one probability of about 1 in 137. The warmth of the room is that probability. The color of whatever light is still on is that probability. The signals moving through your nervous system as you listen to this are that probability, running along the membranes of cells whose structure is held together by the same number. Every part of the experience you are having right now is the same coupling, applied at a rate no one can count, and it has been applied at exactly that strength for as long as there has been anything to apply it to. At which point everyone reaches for the same explanation, and I am going to spend very little time on it, because it is a question large enough to deserve a night of its own, and we have taken it apart at length before. The idea is that constants like this were set more or less at random when the universe cooled, that there are enormously many regions or universes where they were set differently, that almost all of those are sterile, and that we necessarily find ourselves in one of the rare ones capable of producing something that notices. On that account, there is nothing to explain about the value. The value is a selection effect, like being surprised that the planet you were born on happens to have breathable air. The argument is serious, it is held by serious people, and it has a serious problem, which is that it is extremely difficult to test, and that it can be made to accommodate almost any observation. I am not going to relitigate it tonight. I flag it because it is the standard move, and because I want to be clear that it is not the answer this video is heading toward. Here is the reason it is not. The selection argument, even if entirely correct, explains why we observe a value in the habitable range. It does not explain the mechanism that sets values in the first place. It does not tell you why the number is 1 over 137 rather than 1 over 140, both of which are presumably habitable. And critically, it does not touch the thing we uncovered earlier, that alpha is not a fixed dial at all, but the resting position of a curve that ran downward as the universe cooled and stopped somewhere, for reasons nobody can state. A selection argument can tell you why you are in a room with a survivable temperature. It cannot tell you what the thermostat is made of. And that is the question we are going to finish on, because it turns out that the thing we have been calling the fine structure constant all night, this famous unexplained number, is not actually the bottom of anything. It is not a fundamental constant of nature in the way it is nearly always described. There is a layer beneath it, which is why explaining it would mean explaining everything else. For 100 years, the fine structure constant has been described as one of the fundamental constants of nature. It is in the textbooks that way. It is on the physicists' walls that way. And it is, in the strict sense, not true. In the standard model of particle physics, electromagnetism is not a force in its own right. It is one face of a single unified interaction that also includes the weak nuclear force, the force responsible for certain kinds of radioactive decay and for the reactions that let the sun burn. Above a certain energy, those two are not two things. They are one thing, described by one framework, with two separate coupling strengths of its own, neither of which is alpha. What happens as the universe cools is that this unified structure breaks apart, and the way it breaks is governed by a mixing angle, a number that describes how the underlying fields recombine into the ones we actually observe. The electric charge that comes out the other side is built from the two deeper couplings and that angle, and alpha is built from the electric charge. So alpha is downstream. It is not a dial on the machine. It is a reading on a gauge, and the gauge is measuring the combined effect of things further in. This changes the question completely. For most of tonight, the question has been, why is alpha 1 over 137? The real question, the one a working theorist would actually pose, is, why do the underlying electroweak couplings have the values they have, and why is the mixing angle what it is? Its sine squared measured at about 0.231, another pure number nobody can derive. And underneath that is the largest version of the question, which is the one this entire video has been walking toward. The standard model has somewhere between 19 and 26 free parameters, depending on how you count the neutrinos. 19 numbers, at minimum, that the most successful theory in the history of science cannot produce, and simply has to be handed. Particle masses, mixing angles, coupling strengths, every one of them measured, none of them explained, all of them apparently independent of one another. A theory with 19 unexplained inputs is not a final theory. It is a superb description that knows it is standing on something. There is one encouraging precedent here, and it is worth holding on to. The mass of the proton used to be exactly this kind of number, measured, tabulated, unexplained. It is now calculated from the theory of the strong force by running enormous simulations on supercomputers, and the calculation agrees with the measurement. Nobody derived it with a pretty formula. They derived it by having the right underlying theory and enough computing power to grind it out. So there is at least one clear example of a number graduating from the measured column to the explained column, and it happened within living memory. The place people look for the same thing to happen to alpha is the running curve. Take the three coupling strengths of the Standard Model, electromagnetic, weak, and strong, and follow each of them up the energy scale. They all move, and as they move, they converge, heading toward one another at an energy around 10 to the 16th giga-electron volts. In the plain Standard Model, they very nearly meet and then miss. Add supersymmetry, and in certain versions, they meet cleanly. That near miss has been one of the most tantalizing numbers in theoretical physics for 4 decades. Because if the three couplings really are one coupling at high energy, then their low energy values are not independent facts at all. They are one number seen through different amounts of running. Alpha would be explained the way the proton mass was, not by a formula, but by a theory. The trouble is that the collider searches for supersymmetry have come up empty, year after year, and the simplest versions of that picture are now in poor health. The convergence remains suggestive. It has not become an explanation. And that is why explaining alpha would not be explaining a number. To derive alpha, you would need the electroweak couplings. To derive those, you would need whatever fixes the parameters of the Standard Model. To have that, you would need the theory that comes after the Standard Model, the one that says why there are 3 generations of matter, why the forces have the strengths they do, why the mixing angles are what they are, and why any of these things had to be so rather than otherwise. Whoever explains this number will have that theory in their hands. That is the whole of it. Alpha is not one mystery among many. It is the smallest, cleanest, most stubbornly unitless place where the incompleteness of everything we know becomes visible without a telescope or a collider. One number on a wall that the whole edifice cannot account for. Remember what we said much earlier. At the moment, all the units cancelled. This is a number that would survive the loss of everything we invented. Burn the meter sticks, forget the second, abolish the coulomb, and alpha is untouched. When I said that the first time, it sounded like a reassurance. It meant the number is objective, a real fact about the world, not an artifact of how we happen to measure. Hear it again now, and it is not a reassurance. It is a demand. Because if the number contains no trace of our conventions, then there is nowhere to hide. You cannot explain it away as a unit choice. You cannot adjust a definition and make it go tidy. There is no committee that can vote on it. It is simply, flatly there, and the theory has to account for it, or admit that it cannot. And for 100 years, it has been admitting that it cannot. And I want to leave you with the sharpest possible version of how live this is right now, because this is not a historical puzzle sitting quietly in a drawer. Alpha is measured today by recoiling atoms. You have an atom absorb photons, measure the kick with extraordinary precision, and extract the number. In 2018, a group at Berkeley did this, with cesium, and got the inverse of alpha, as 137.0359999046, to about 2 parts in 10 billion. In 2020, a group in Paris did it with rubidium and got 137.0359999206 to 81 parts per trillion, the most precise measurement of this number ever made. Those two results do not agree. They differ by more than 5 standard deviations. In a field where 5 standard deviations is the threshold for announcing a discovery, 2 of the most careful measurements ever performed disagree at discovery-level significance about a quantity that is supposed to be the same everywhere in the universe. One of them contains a mistake nobody has found. That is the only available explanation, and neither group will guess which. Now recall the electron's magnetism, the most precisely tested prediction in the history of science, agreeing with theory to about 1 part in a million. To make that comparison, you have to feed a value of alpha into the theoretical side, feed in the rubidium value, and theory and experiment agree beautifully. Feed in the cesium value instead, and a gap opens up, small but real, of the kind that would mean the electron is quietly telling us about physics beyond the standard model. So the question of whether the humblest particle we know is currently pointing at undiscovered physics depends entirely on which of two laboratories has an unnoticed error in the 5th decimal place of a number that nobody can calculate. That is where we are, 110 years after a man in Munich found it hiding in the gap between two red lines, 75 years after Feynman told everyone to put it on the wall, 68 years after Pauli died in room 137 with the question unanswered. We can measure it to 81 parts per trillion. We can watch it change with energy and predict the change exactly. We can trace it back 1.7 billion years through a reactor that ran itself in Gabon and out to the far side of the observable universe through the light of quasars, and find it unmoved in both directions. We built the modern world on knowing it, and we cannot say why it is what it is. There is something almost restful in that, if you let it be. Not every question in physics is a problem waiting to be cleared away. Some of them are markers. This one has been sitting in the same place for a century, perfectly precise, perfectly stable, perfectly unexplained, waiting for a theory that has not arrived, and it will keep sitting there, patient and unbothered, holding your hand above the blanket and the atoms of your body together, whether or not anyone ever works it out. Thank you for spending this time with me, drifting through one small number and everything that hangs from it. If this kind of slow, unhurried exploration is how you like to end your day, a like or a subscribe would mean a great deal. It is what keeps these long nights possible. And remember, the next time you rest your hand on something solid and feel it hold, that is one chance in 137, repeated more times than anyone can count, and nobody knows why it is that and not something else. Good night, and may the number keep you company.